Grounding requirements for gas meters are essential for safety. According to the National Fire Protection Association (NFPA) Code 54, gas meters must be grounded to prevent the buildup of static electricity or lightning strikes. The grounding electrode must be capable of handling the maximum fault current from the electrical service. The grounding conductor must be sized to the fault current. When considering grounding options, in the described situation, two possible grounding options are present. Firstly, ground to the electrical panel. Run a grounding conductor from the gas meter to the electrical panel. Ensure the grounding conductor is sized according to the fault current. This is a preferred method if the electrical panel is within a reasonable distance of the gas meter. Secondly, ground to the furnace. Run a grounding conductor from the gas meter to the furnace. The furnace must have a grounding electrode connected to the electrical panel. Ensure the grounding conductor is sized according to the fault current between the gas meter and the furnace. There is no specific distance requirement for grounding from the gas meter. However, it is best practice to keep the grounding conductor as short as possible to minimize resistance. In the described situation, either grounding option is acceptable. If the electrical panel is relatively close to the gas meter, grounding to the panel is preferred. Otherwise, it can be grounded to the furnace if it has a proper grounding electrode. Ensure the grounding conductor is sized appropriately for the fault current. When dealing with electrical grounding, several factors must be considered to ensure safety and compliance with electrical codes. Understanding the purpose of grounding, different grounding methods, and the importance of proper conductor sizing is crucial. Grounding in electrical systems provides a low impedance path for fault current to return to the source, which helps to quickly trip a circuit breaker or fuse, preventing electrical shock hazards and equipment damage. Grounding also helps to stabilize voltage levels and reduce electrical noise in sensitive electronic equipment. The National Electrical Code, or NEC, outlines specific requirements for grounding electrical systems. These requirements are designed to ensure that grounding systems are effective in protecting people and property from electrical hazards. It is essential to consult the latest version of the NEC and local electrical codes for specific requirements in your area. There are several different methods for grounding electrical systems, including grounding to a metal water pipe, grounding to a ground rod, and grounding to a building steel structure. Each method has its advantages and disadvantages, and the appropriate method will depend on the specific application and local code requirements. Grounding to a metal water pipe is a common method, especially in older buildings. The water pipe must be metallic and in direct contact with the earth for at least 10 feet, or 3.48 meters. The grounding conductor is typically connected to the water pipe using a grounding clamp. It is essential to ensure that the water pipe is continuous and not interrupted by any insulating couplings or sections. Grounding to a ground rod involves driving a metal rod into the earth and connecting the grounding conductor to it. Ground rods are typically made of copper or copper-clad steel and must be at least 8 feet, or 2.438 meters, long. The ground rod must be driven into the earth so that at least 8 feet of it is in contact with the soil. Multiple ground rods may be required in areas with high soil resistivity. Grounding to a building steel structure is an option in buildings with a structural steel frame. The steel structure must be effectively grounded to the earth. The grounding conductor is typically connected to the steel structure using a grounding clamp or by welding. The size of the grounding conductor is critical to ensure that it can safely carry the maximum fault current. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. For example, according to NEC Table 250.122 for 20 amp circuit, the minimum size of the grounding conductor is 12 AWG copper. For a 60 amp circuit, the minimum size is 10 AWG copper. For a 100 amp circuit, the minimum size is 8 AWG copper. It is crucial to use the correct size grounding conductor to prevent overheating and potential fire hazards. Bonding is another essential aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a low impedance path for fault current. This includes metal enclosures, conduits, and equipment frames. Bonding helps to ensure that all metal parts are at the same potential, reducing the risk of electrical shock. The NEC provides specific requirements for bonding electrical systems. These requirements include the use of bonding jumpers to connect metal parts together and the proper sizing of bonding conductors. It is essential to follow these requirements to ensure that the bonding system is effective in protecting people and property from electrical hazards. In addition to grounding and bonding, surge protection is another important consideration for electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are available in a variety of types and sizes, and the appropriate SPD will depend on the specific application and the level of protection required. SPD can be installed at the service entrance of a building or at individual equipment locations. When installing SPD, it is essential to follow the manufacturer's instructions and local electrical codes. Regular inspection and maintenance of grounding systems are crucial to ensure their continued effectiveness. Grounding conductors and connections should be inspected periodically for corrosion, damage, and loose connections. Ground rods should be tested to ensure that they are providing adequate grounding. If any problems are found, they should be corrected immediately. In summary, grounding is an essential aspect of electrical safety. Understanding the purpose of grounding, different grounding methods, and the importance of proper conductor sizing is crucial. By following the requirements of the NEC and local electrical codes, it is possible to create a safe and effective grounding system that protects people and property from electrical hazards. Furthermore, it is important to distinguish between grounding and bonding, as they are related concepts with distinct roles in electrical safety. Grounding, as discussed, provides a path for fault currents to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers or fuses. Bonding, on the other hand, connects non-current carrying metal parts to create an equipotential plane, minimizing voltage differences and reducing the risk of electric shock. The NEC mandates specific requirements for both grounding and bonding, and compliance is crucial for ensuring electrical safety. For instance, NEC Section 250.4 A5 requires that normally non-current carrying metal parts of electrical equipment be connected together into the electrical supply source in a manner that establishes an effective ground fault current path. This path must be permanent and continuous, have adequate capacity to safely conduct any fault current likely to be imposed on it, and have sufficiently low impedance to facilitate the operation of overcurrent protection devices. Similarly, NEC Section 250.96 specifies that metal enclosures containing service conductors or equipment must be bonded to the grounded conductor. This bonding ensures that any fault current flowing through the enclosure will have a low impedance path back to the source, causing the overcurrent protection device to trip quickly. In the context of gas meter grounding, it's important to note that the grounding conductor should be connected to the gas piping system on the customer side of the meter, not directly to the meter itself. This is to prevent the possibility of stray currents flowing through the meter and potentially causing corrosion or damage. The grounding conductor should be sized according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the electrical circuit that supplies the gas-fired appliance. The connection should be made using a listed grounding clamp or fitting that is suitable for use with gas piping. Furthermore, it is crucial to ensure that the gas piping system is properly bonded to the electrical grounding system of the building. This bonding helps to create an equipotential plane and minimize the risk of electric shock. The bonding conductor should be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The connection should be made using a listed bonding clamp or fitting that is suitable for use with gas piping. In addition to the NEC requirements, local codes and regulations may also apply to gas meter grounding. It's important to consult with local authorities to ensure that all applicable requirements are met. When grounding to a furnace, it's essential to verify that the furnace has a dedicated grounding electrode conductor connected to the electrical service grounding system. This grounding electrode conductor should be sized according to NEC Table 250.66 and connected to a grounding electrode system that meets the requirements of NEC Section 250.50. If the furnace does not have a dedicated grounding electrode conductor, it may be necessary to install one. This can be done by running a grounding electrode conductor from the furnace to a nearby ground rod or to the building's main grounding electrode system. The grounding electrode conductor should be sized according to NEC Table 250.66 and connected to the grounding electrode system using a listed grounding clamp or fitting. When grounding to the electrical panel, it's important to connect the grounding conductor to the grounding busbar in the panel. The grounding busbar is a metal bar that is connected to the grounding electrode system. The grounding conductor should be sized according to NEC Table 250.122 and connected to the grounding busbar using a listed grounding connector. It's also important to ensure that the electrical panel is properly bonded to the building's metal water piping system or to a suitable grounding electrode. This bonding helps to create an equipotential plane and minimize the risk of electric shock. The bonding conductor should be sized according to NEC Table 250.66 and connected to the water piping system or grounding electrode using a listed bonding clamp or fitting. When working with electrical systems, it's essential to take appropriate safety precautions. Always turn off the power to the circuit before working on it. Use insulated tools and wear appropriate personal protective equipment such as gloves and safety glasses. If you're not comfortable working with electrical systems, it's best to hire a qualified electrician. In addition to the above considerations, it is important to address the specific scenario of a gas meter located 60 feet or 18.288 meters from the electrical panel and under a carport with concrete surroundings. In this situation, several factors must be taken into account when determining the best grounding method. The distance between the gas meter and the electrical panel is a significant consideration. While there is no specific distance limitation in the NEC, it is generally recommended to keep the grounding conductor as short as possible to minimize impedance and ensure effective fault current flow. In this case, 60 feet may be considered a relatively long distance, which could increase the impedance of the grounding conductor. The concrete surroundings of the carport also present a challenge. Concrete is not a good conductor of electricity, so it cannot be relied upon as a grounding path. Additionally, the presence of reinforcing steel in the concrete, also known as rebar, may complicate the grounding situation. Rebar can act as a conductor, but it is not always reliably connected and may not provide a consistent grounding path. Given these factors, the best grounding method for this gas meter may depend on several considerations. Firstly, if the furnace is located closer to the gas meter than the electrical panel, grounding to the furnace may be the preferred option. As long as the furnace has a dedicated grounding electrode conductor connected to the electrical service grounding system, this method can provide a reliable grounding path. Secondly, if grounding to the furnace is not feasible, it may be necessary to install a dedicated ground rod near the gas meter. This ground rod should be driven into the earth as close to the gas meter as possible, and the grounding conductor should be connected to the ground rod using a listed grounding clamp. Thirdly, the size of the grounding conductor should be carefully selected based on the size of the overcurrent protection device protecting the electrical circuit that supplies the gas-fired appliance. NEC Table 250.122 should be consulted to determine the appropriate conductor size. Fourthly, the grounding conductor should be routed in a manner that minimizes its length and avoids sharp bends or kinks. The conductor should be protected from physical damage by running it in conduit or other suitable enclosure. Fifthly, all connections should be made using listed grounding connectors and fittings that are suitable for the application. The connections should be clean and tight to ensure good electrical contact. Finally, after the grounding system is installed, it should be tested to verify its effectiveness. A ground resistance tester can be used to measure the resistance between the grounding conductor and the earth. The resistance should be low enough to ensure that fault currents can flow effectively. In addition to these considerations, it is important to be aware of any local codes or regulations that may apply to gas meter grounding in the specific location. Local authorities should be consulted to ensure that all applicable requirements are met. In summary, grounding a gas meter located 60 feet from the electrical panel and under a carport with concrete surroundings requires careful consideration. The distance, concrete surroundings, and potential presence of rebar are all present challenges that must be addressed. By following the recommendations outlined above and consulting with local authorities, it is possible to install a safe and effective grounding system that protects people and property from electrical hazards. Furthermore, it is crucial to understand the role of the equipment grounding conductor, or EG, in providing a low impedance path for fault current to return to the source. The EGC is a critical component of the grounding system and must be properly sized and installed to ensure effective fault current flow. The NEC specifies the requirements for EGC in section 250.118. This section outlines the types of conductors that are permitted to be used as EGC, including copper, aluminum, and steel. The EGC must be sized according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the circuit. The EGC must be installed in the same raceway or cable as the circuit conductors. The EGC must be connected to all metal enclosures, equipment frames, and other non-current carrying metal parts of the electrical system. The EGC must be connected to the grounding electrode system at the service entrance or at the source of a separately derived system. In the context of gas meter grounding, the EGC plays a critical role in providing a low impedance path for fault current to return to the source in the event of a fault in the gas-fired appliance. The EGC should be connected to the gas piping system on the customer side of the meter, as discussed earlier. The EGC should be sized according to NEC Table 250.122, based on the size of the overcurrent protection device protecting the electrical circuit that supplies the gas-fired appliance. The EGC should be installed in the same raceway or cable as the circuit conductors that supply the gas-fired appliance. The EGC should be connected to the grounding electrode system at the service entrance or the source of a separately derived system. In addition to the EGC, it is also important to understand the role of the grounding electrode conductor, or GEC, in connecting the grounding electrode system to the electrical system. The GEC is a conductor that connects the grounding electrode system to the neutral busbar in the service equipment or to the grounding busbar in a separately derived system. The GEC must be sized according to NEC Table 250.66, based on the size of the service entrance conductors or the size of the conductors of the separately derived system. The GEC must be installed in a continuous length without splices or joints. The GEC must be protected from physical damage. The GEC must be connected to the grounding electrode system using a listed grounding clamp or fitting. In the context of gas meter grounding, the GEC plays a critical role in connecting the grounding electrode system to the electrical system, providing a path for fault current to flow back to the source. The GEC should be connected to a grounding electrode system that meets the requirements of NEC Section 250.50. This section outlines the types of grounding electrodes that are permitted, including metal water pipes, ground rods, ground rings, and building steel structures. The grounding electrode system must be effective in providing a lower impedance path for fault current to flow back to the source. In addition to the EGC and the GEC, it is also important to understand the role of bonding jumpers in connecting metal parts of the electrical system together to create an equipotential plane. Bonding jumpers are conductors that connect metal enclosures, equipment frames, and other non-current carrying metal parts of the electrical system together. Bonding jumpers must be sized according to NEC Table 250.102 based on the size of the circuit conductors. Bonding jumpers must be installed in a manner that provides a low impedance path for fault current to flow. Bonding jumpers must be connected to the metal parts using listed bonding connectors or fittings. In the context of gas meter grounding, bonding jumpers play a critical role in connecting the gas piping system to the electrical grounding system, creating an equipotential plane and minimizing the risk of electric shock. Bonding jumpers should be used to connect the gas piping system to the electrical grounding system at the service entrance and at any other points where the gas piping system is likely to come into contact with metal parts of the electrical system. In conclusion, grounding a gas meter requires a comprehensive understanding of the NEC requirements for grounding, bonding, and equipment grounding conductors. By following the recommendations outlined above and consulting with local authorities, it is possible to install a safe and effective grounding system that protects people and property from electrical hazards.